no-no. Why why fourth moment is a no-no? The reason is that everybody still believes Phillips. If you believe in Phillips, then the spectrum has a -5. If you compute the fourth moment of -5, the omega frequency is 1 over omega fifth. Then you compute the fourth moment, you have omega to the fourth times omega -5. You get 1 over omega d omega. 1 over omega d omega has a logarithmic singularity when omega approach to infinity, because 1 over omega d omega is log omega. When omega becomes large, then it becomes infinite. So the value, this value, then it's totally determined by the cutoff frequency. Now, because it depends on cutoff frequency, you can decide, so wherever a cutoff, you get a different answer. So therefore, people think that any value, any expression with omega to the fourth cannot be evaluated. Yeah. So people will never use it because of the lack of the proper spectrum form. Yeah. So this form, if we use this form, and we make a comparison with the observation, this is the theoretical value, and you can see that this is frequency, this is amplitude. It's even more skewed than Langevin-Higgins. Why? Because this has a much wider spectrum bandwidth. It can apply to a much smaller wave. So the asymmetry is stronger. And you compare this theoretical with observation, you find that this also looks very good. So there are different kind of spectrum shape, probability density function. Now, if we go ahead and check this, you see that if you integrate the H out, you get a marginal distribution of sigma, and from marginal distribution of sigma, you actually can get the period distribution. And period distribution compared with the delta looks also very nice. But you have to realize, at that time, either Langevin-Higgins or Dr. Yuan's distribution are all relatively narrow band, because at that time we don't have the empirical mode decomposition. So if a wave has more than one peak, you will have problem. So most of their waves actually is built based on almost a intrinsic mode function. The difference is that the intrinsic mode function can have frequency wider or narrowly distributed. Yeah. So the comparison, if you neglect the small wave, the comparison with the large wave, the distribution looks good. Having seen that, then I decide to carry out the test. I said, all right, I will then use this sigma square and to integrate, and I will see how it looks, how the distribution, that weighted distribution of as a function of sigma, how that looks. And once you carry out the integral, and the integral can actually be carried out in a closed form, even though this seems ugly, but typically it's an exponential function. The integral can be carried out easily. And once you carry it out, what you find is that this is the frequency. This frequency is to the second power. A frequency to the second power, but then here is a -5 over 2. So this 2 and 2 cancel, so you get the frequency -5. So Langevin says, well, look, listen, this is correct. This is -5. It's a Phillips spectrum. Of course, Langevin never did this. I did this. I was found this -5. I said, well, looks good. Yeah. That's one way of doing that. And the next way to do that is using Dr. Yuan's. And Dr. Yuan's integral, again, is just a power law if you carry out the integral. This is much more complicated. Here is that you have a sigma square. Sigma squared squares is sigma fourth. Sigma fourth raised to 5/2 law, it becomes sigma to the 10th. Then luckily you have a sigma 3 here. So it's sigma minus 7. It's not sigma minus 5. In other words, asymptotically, it does not agree with Phillips. Yeah. But this is the form. And this form, again, depends upon moment to the fourth. Yeah. So we got two different forms, but both form looks looks like a polynomial function, and we can actually compare with observation. This is the original spectrum, and here are two curves. One is Lange-Higgins, the other one is Yuan. Even though the asymptotic value is slightly different, but if you plot it in a linear scale, you will never see it. Yeah, they both compare well with with the spectrum. But the difference is that the spectrum derived with probability density function is a little bit more symmetric compared to this spectrum is very asymmetric from the peak. But the probability density function derived the spectrum is much more symmetric. And especially if you look at the curve by Lange-Higgins, because it's much narrow band and therefore it's much more symmetric. Yeah. And if you use Yuan's formula, we have a little bit deficiency, and this little bit deficiency we may not totally attribute to the inaccuracy of the model, because this is a Fourier spectrum, and we all know Fourier spectrum has harmonics. So once beyond the peak, this value may not be physical; it may be mathematical. So I made a couple of comparisons. They all look about the same. Yeah. So I think the connection between the probability and the spectrum can be obtained from this operation. And this again, then if I define moments to the nth power, if I carry out this, I can check how well this model behaves. Now, so these moments can be established as the moments as this bandwidth parameter derived before. As bandwidth parameter approach to 1, that means it becomes a very narrow band. Then the spectrum you define this way, all the moments approach to the true moments of the spectrum shape. So that is comforting in the limited case when the spectrum is a narrow band. But for a wider band, such as white noise, the ratio of the moments defined by frequency and moments defined by probability, we have only the first moment equal to 1. That means zeroth moment. That means the total energy, everybody agree, because that's where we started. We started with the expected value of elevation equals to the joint distribution. The second moment already is off. And the third, fourth moment is even worse. Yeah, the ratio is the spectrum defined by Fourier. It's much wider than the spectrum defined by the probability density function. Yeah. Why is that? Because the Fourier spectrum indeed can apply to a wider band. and all the probability density function are all applied to a narrow band. And especially all this formula is derived from amplitude. Amplitude means the envelope. And if you can establish an envelope, the only envelope that will make sense is when you have a intrinsic mode function. So in between extrema, you can only have one zero crossing, and in between zero crossing, you can have one extrema. And if you do not have that, then the envelope cannot be defined meaningfully. Yeah. For example, you have all this jiggled surface, and you connect all the maximum, and the maximum will follow the mean wave. Yeah, because everywhere you have maximum. So with this, we reach the conclusion that there is a connection, but the connection is only work for narrow band, extremely narrow band. Now, getting here, we can draw a short conclusion. The conclusion is that there is a relationship between probability density function and spectrum based on Fourier analysis. And this relationship exists only for energy containing waves, only for large waves. If you start talk about the small waves, it will not work. Yeah. The Fourier spectrum works for much wider bands than the probability density function, which are all derived under narrow band or near narrow band. Yeah. So it is comforting that we established this relationship. And once I finish this, I was very happy. I thought, well, at least I understand the spectrum, the asymptotic form. I understand the probability density function. I was able to connect the two, and I wrote a paper to summarize this. Then I start to turn my attention to a different direction. And that's a turning point in my research. Perhaps I shouldn't use this. I was trying to change it, but it's kind of late. It's a turning point in my life. Yeah. At that time, I noticed that I need to study the governing equation of the wave, because we need the amplitude, we need the envelope, and what actually governs the envelope. Yeah. And that envelope is governed by Schrödinger, nonlinear Schrödinger equation. So I decided to look into that. And when I look into that, I have to look back in the history, how this thing arrived. Since the water wave is amazing. Water wave is one of the first natural phenomena that was successfully described by mathematics. Yeah. All the others, say for example, is how the wind blows. You have to wait until we have a huge computer or whatever. Otherwise, you cannot solve that equation. But the water wave can be treated very well because the viscosity or whatever doesn't matter. Does not matter that much. You can treat the fluid as a perfect fluid. Once you treat the wave as a perfect fluid, the wave is a potential solution, like electromagnetism. Yeah. So that becomes very easy to treat, or relatively easy. I should not say very easy. So a lot of mathematicians work in water wave. Even nowadays, if you survey the world scene, you find that most of the people that study wave successfully are all applied mathematicians. Yeah, Jerry Wheaton, J.B. Keller from Koran, Jerry Wheaton from Caltech, and you go to a big name, George Stokes. We'll come back to talk about. They're all mathematicians, and they can use mathematics to describe this phenomenon. Yeah, so the first wave phenomenon, actually, well, people know wave of course, people ever since the history immemorable long, people know waves. How do we know people know waves? You don't have to look very far. Go to any museum, you find the old pottery. Yeah, lots of pottery has a wavy form. Where you get the impression? It has to look at the water. The water has a wave, and the wave looks pleasant. So they put the wavy pattern on pottery as a decoration. So people has noticed the wave for long time. Yeah, but the people try to describe it scientifically. Start from Russell, John Scott Russell. Russell in 1834, he was riding a horse along a canal bank, and a barge came through. Then he found that when the barge moved, in front of the barge there was a solitary wave. It's one push of the wave. This one hump. This wave is just one hump, and propagated very fast. And he ride the horse and follow the wave for miles. The wave is still there. And he was so amazed. He went back and did a lot of experiment. And that's okay. Once he finished his experiment, he made a report 10 years after he made the initial observation. 1844, he went to British Association of Advancement of Science, like our AAAS. Yeah, made a report, and the reception he got was very bad. Yeah, the people really does not believe him as Stokes. Yeah, and as a result, even though he is a fellow of Royal Society, he never get any paper published in the Royal Society, even at his death, because the wave he described, George Stokes, this is not possible. Yeah, George Stokes, he derived the deep water periodic wave, and he published that in 1847, and that is the classic paper that we all know. Now, before we get into Stokes, let's look at the shallow water. The shallow water wave, as I said, his experiment and observation were totally discounted by George Stokes. He thinks that the mathematics doesn't support that. Until very late, 1871, Boussinistic and Rayleigh start to say, well, maybe his observation is right if we use different way to describe it. And the really important breakthrough is 1895. Yeah, by 1895, Cordwick and DeWolf derived the KdV equation, and that was able to establish that such equation can have a different set of governing equation. Yeah, and the real solution of this KdV equation will have to wait until 1960s by Krosko. Krosko is let me see. I think he's a mathematician in Princeton, and he derived or later we'll come back. He actually found a closed form solution. Now this is all history, and the closed form solution for KdV equation was called soliton. This is called soliton. The reason it's called soliton is that solution that they got actually propagate almost like a particle. You can have one soliton propagate, another soliton propagate, and these two particles can propagate independent of each other with very little interaction. And so because of that, this wave, even though he called the soliton, but lots of other people think that, well, soliton only applied to that particular equation. So most of people still call it a solitary wave. Yeah. Then his contribution of finding a solution, closed form solution, to a physically derived nonlinear differential equation was so amazing that he got a lot of honor, yeah, including the National Medal of Science, yeah. And in 1993, and the citation is for his influence as a leader in nonlinear science for more than 2 decades, yeah, and principal architect of the theory of soliton solution of a nonlinear differential equation of evolution. So that's very, very big. Now you can see that an original observation of a phenomenon was discounted by the leading scientists of the day. Eventually becomes the mainstream. Yeah. Solitary wave, soliton equation has many, many different forms. We can have sine-Gordon equation. We have the sine function. We can have a cubic Schrödinger equation. We can even have still different solution equation. And this equation is spatial, has x and y variable, and this actually is the nonlinear term. Actually, this equation eventually one of the exact solution form was found by I forgot his name anyway. Not only that, he's a mathematician. That's one of the few mathematicians actually did an experiment, and he found that this solution of this wave is a hexagon wave. Yeah. The classic solitary wave is actually of this form, and this form, this is nonlinear. This is the KdV equation, and the solution is hyperbolic secant. Yeah, it's a single hump in the field. At this single hump in the field, you can have one wave here, one wave here, and this wave can catch up with it, and getting closer and getting together, and then eventually pass and go beyond. Leave this wave totally undisturbed. Yeah, that's the amazing part of the solitary wave. And can we see, other than this example? Yes, many people see this kind of picture on the beach when the very shallow water comes in. Watch this. This water comes in. This water comes from that way, and these are two solitary waves. These two solitary waves cross each other. Yeah. But after the cross, see, this part has already been crossed. It still keep propagating. Yeah. So the two sides cross each other, and this has not been crossed, and this this has not been crossed. Once it crosses, it's over here, over here. Yeah. So the solitary wave, it's really like a particle. It just maintains its own integrity and keep propagating. There is a slight phase shift. It is a 1/2 wave phase shift. But other than that, the wave actually merge from interaction without any without any change. Many people now, since this is soliton solution, describe nonlinear evolution. Recently, people even think that that galaxy actually behave like that. See, one galaxy meet another galaxy, they just move right across and can merge from the other side without even lost their stars. And that's amazing, because galaxy is supposed to be governed by its own force, and or gravitational force. When these two gravitational forces get together, it can still remember which star belongs to which galaxy and and propagate out. But of course, nobody observed that. People think that should be the way. Anyway, the solitary wave has all different form. This is another picture. The first picture is on the beach. Everybody can see. This picture is actually from satellite. Yeah. From satellite, you look at the ocean surface. What you see is not really a bump. What you see is really a surface roughness change, surface roughness pattern change. And these are internal solitary wave. It's created by tide. And the wave, the water surface flat. And the water surface, ocean surface has different density. So there's a layer of the surface layer. The temperature is usually high compares to the lower lower main body of the ocean. This is called the thermocline. And when you have a disturbance, the thermocline start to oscillate. And because of the density difference in the across the interface, is only of the order of parts per thousand. Yeah. So this amplitude can be very large. As it oscillates up and down very large, it drives the water particle to move. So they create convergence and divergence surface current. And that convergence divergence surface current is visible. The convergent divergent surface current influences small waves. The small waves, this is not big wave. The small wave that comparable to radar wavelengths, it's a centimeter range. So using radar, you actually see this pattern. You go over there, you don't see it. You do not see a hump on the surface. You see the roughness change. So we can see that see this pattern. This actually is tidal induced solitary wave, and you can also see this very regular solitary wave in the ocean. And this wave is definitely not a sign. There's one bump and flat, another bump, flat, another bump. So elevation can also have that. So the shallow water wave, the governing equation. And what are the assumptions that are made? So this is where I picked up. We have the KdV equation. Then the question is that if we let this u, which is the velocity field, if we let u to be equal to amplitude times ei theta, plus second order plus third order and higher order, and if we plug this back in here, then we have a perturbation analysis. This is how I first was exposed to the Schrödinger equation. Then you can derive. Then if you assume this theta, which is the phase function is omega k dot x minus omega t. Yeah, and you're assuming that k is constant, omega is also constant. Assuming omega and k both constant, then you can plug it back and you derive. You find that you do have a cubic nonlinear term, and that becomes the cubic nonlinear Schrödinger equation. You derive this based on this amplitude and this phase has to be constant, not constant to the third order. What do you mean constant to the third order? That means the constant, if I take derivative, it's still constant. I take it second derivative, still constant. Yeah, so it's very, very constant. In other words, everybody, when people derived this, people get very excited. Yeah, why do people get excited? Because people then think that if I write my wave as a sinusoidal, this is a sinusoidal solution. If I write a sinusoidal solution, this amplitude is governed by a cubic nonlinear equation. Yeah. So this equation, this solution, that means the water wave itself may not be soliton, but the group, the envelope, will be soliton. So it's called the envelope soliton. Yeah. When people get this, water wave people say, aha. You see, Schrödinger is a Nobel Prize in quantum mechanics. Now water wave get elevated to the quantum level. Yeah, and we have the same differential equation. So they get very excited. And most of the in United States, people are doing this way, yeah, by perturbation. But you can see that if I assume, so what if the frequency is not constant? Yeah. So if frequency is not constant, then if you say that the frequency is the second order, in other words, it's constant, all right, but the derivative is now small. Yeah. If you assume that, then the derivative cannot be left out, cannot be neglected. Then you get a very different differential equation. Still cubic, nonlinear, but you will start to have the change of frequency or change of wave number. Yeah. And you can even go say, so well, what if the frequency is not constant by itself? Not only its derivative, its frequency is not constant. Then you will have even more extra terms in there. So when I start to play with this equation, I derive this equation, I find that there's no stop. Is frequency constant or is not? But then at that time, I didn't know frequency is not constant. I thought the frequency is perhaps constant. But then I also start to suspect that the constant frequency implies a pure sinusoidal wave. And we know that the pure sinusoidal wave does not exist. So what is exactly the frequency? That makes me think that what frequency actually means. And how to get that frequency? You have to go to Hilbert transformation. From here, I start to see the importance of amplitude and importance of frequency. And not only that, I want to see the instantaneous value of frequency. And frequency has to be a differentiable value. And then I realized the Fourier doesn't work. Fourier is constant. Yeah. And the Fourier is not a physical wave. So even if I derive an equation, I'll govern a sinusoidal wave. That's not a physical entity. That's a mathematical entity. Sine wave, you can write the sine wave solution anytime. But sine wave will never exist because it doesn't satisfy all the kinematic or dynamic boundary conditions. So at this time, I start to look into a different way to look at the frequency. Yeah. Meanwhile, most of my work were in deep water wave. Deep water wave, as I said, at the beginning was the mainstream because Russell get pushed aside, even though nonlinear Schrödinger equation now becomes the mainstream, more sophisticated answer. But at the very beginning, Stokes is the one that called the shots. Stokes is not a regular mortal. He is a giant in science. Look at what what his position. He's a Lucasian professor. Lucasian professor is the chair that Newton occupied. Yeah, Newton's teacher was the inaugural chair, but he occupied that only for a couple of years. Then he found that Newton is much more capable, so he gave the chair to Newton. Newton was only in his 20s. Yeah, so Newton occupied this. Newton occupied this chair all the time he was in Cambridge. But then this apparently the chair professor pay is not very good. So Newton later used all kinds of different relationship and get a much better job. The job he got was the mint, just make coins. Yeah. So Newton is a very smart person. Once he becomes the he's not a master. He's just the superintendent. Master is make lots of more money. So each coin they made, the master take a portion. But Newton is just the superintendent. He was very diligent in trying to catch people counterfeiting, make a false coin. Not only that, at the beginning, many people take the coin and go back using a lathe to cut a ring, to shave the coins. This is a coin like this. They cut the layer out. So he collect this metal, like either silver or gold or whatever. So they keep on cutting this. So the coin becomes smaller and smaller, but it's still coin, right? But so they get money that way. Newton was so mad. But how can you prevent that? So Newton invented a way to make the coin side has grooves. That's Newton invented. Yeah. So if you shave the coin, becomes smooth. The smooth is no good. You have to have this groove. Yeah. Anyway, that's the Lucasian professorship. Not only that, he's the president of the Royal Society. Yeah. He actually has the same position as Newton has. Newton was the president, was the Lucasian professor, and he has all that. And he is a mathematician of the first rate. He invented Stokes theory. The double integral becomes cubic integral. That's he invented. Yeah. He was in Cambridge, and Nevers-Stokes equation forever govern all the fluid mechanics. Everybody in fluid mechanics has to know Nevers-Stokes equation, which is the real equation. Consider viscosity and consider all the other terms. So he's such a giant. Therefore, when he said something, people listen. Yeah. Now his wave is start from that time. His wave is called the Stokes wave. The Stokes wave is derived in 1847. As I said, the basic form is a cosine theta becomes 2 theta, 3 theta, 4 theta, and so on and so forth. Yeah, and the theta is k dot x minus sigma t. This is derived a periodical wave. At that time, people think that the periodical wave can also have permanent shape. Yeah, and in fact, he found a solution. This is a periodical wave of permanent solution, and that's why when Scott Russell came up and said, "I found just one wave propagate." Stokes and Airy look at the equations. It cannot be. I mean, if you want to be permanent, it has to be sinusoidal. And here's the solution. And since your wave doesn't fit this, so your wave cannot be true. Yeah. So that's essentially the logic. Yeah. And this is very, very important, and it's very impressive at that time, because if the Stokes wave becomes a standard solution for 100 years, it describes nonlinear properties. See, if I have a cosine wave, this is a cosine, this curve is cosine, this curve is cosine, and this is cosine 2 theta, this is cosine theta, this is cosine 2 theta. And if you add the cosine theta and the cosine 2 theta, you get this this wave. Add these two together, you have this solution. I tried to draw that solution on the board the other day, but I decided to draw it neater. Now this wave is very different from your cosine, because see, over this range, the wave profile is lower than cosine. Over this range is higher, because here the second harmonics fill up here, second harmonics take over and fill up here, and take away, fill up here. So you have now an asymmetric surface. And this asymmetric surface, if you add more terms, and it will make the asymmetry even more pronounced. Yeah. Actually, I only add 2 terms. You already see the peak is higher and the trough is round off. And imagine you add 128 terms. Yeah. And in fact, by the 1960s, this is perturbation analysis. Perturbation analysis in the 60s is a big thing. Okay. So in the late 1960s, there was one person called Dr. Howard at the Axon Research, he actually make the expansion to 128 terms. That's a record. Nobody else tried ever after that. And by the time you add 120 terms, this side becomes a sharp corner. Yeah. So it's totally approached the limit of 120 degrees. So Stokes, with that simple expansion, was able to explain the wave to such a minute detail to even tell you the surface can be asymmetric. And that's amazing. However, at that time, nobody asked the question. The water wave is dispersive. This large wave, the dispersed should propagate faster. This wave should propagate slower. But if you make these two propagate at different speed, you will never get back this solution. These two waves will have to propagate with the same velocity, phase velocity, and not only that, the phase locking, the phase relationship cannot alter. And no physical wave can behave like that, because if water wave is dispersive, if I have a wave of twice the frequency, I should propagate at 1/4 of the phase velocity, but it does not, according to this. So this wave obviously is not a physical wave. This is a beautiful mathematical solution, but it's not physical. Yeah, and that make me even feel even more curious about the water wave solution. Yeah, but then people start to question. For 100 years, from 1847 until 1960, nobody questioned the permanent shape. And then in 1960, Professor Phillips published a paper. The paper is on the dynamics of unsteady gravity wave of finite amplitude. Yeah. He said that the wave is permanent shape, all right. But how can this wave propagate, and how's the envelope, how's the wave as a group, how would they behave? Then by that, he derived a formula, and the formula has wave-wave interaction. Different waves can interact each other and create something different. That paper, of course, caused a lot of interest, but that's not as interesting as the second events. Just at that time, Professor Phillips derived a third-order nonlinear, very weak nonlinear. The people say, well, weak nonlinear perhaps is not important. Okay, it's beautiful math, yeah, but it may not be real. But at that time, the British National Physical Laboratory built a wave tank. Okay, everybody think that a wave should have a permanent shape. They built a wave tank, try to do shipbuilding research. So they built a tank. They want to create a permanent wave of permanent shape. And to their surprise, they generated a wave very, very regular. By the time it propagated about 200 feet, the wave disintegrated. So the National Physical Laboratory refused to pay the builder. They said, you didn't build a good enough tank. Either the tank is no good or a wave maker is no good. Okay, so I will not pay you unless you can make the wave propagate just like this all through the tank. They tried as hard as they can. They cannot do it. Okay, becomes almost end up in the court. The National Physics Laboratory is big. This is a big government organization. They said, well, I'm not going to pay you for this shady job you did. When they were arguing, a professor at Cambridge, Brooke Benjamin, and he start to study wave. He says, let's study the Stokes wave and to see whether Stokes wave is stable or not stable. And so he derived with his colleague Fair. The two of them derived wave instability. What did they find is that the wave of this shape, of Stokes shape, is unstable. Yeah, eventually it will disintegrate. And after they derive that, and what they find is that that instability actually is a particular form of nonlinear wave-wave interaction. So that makes Phillips' study even more important because it is much more general wave-wave interaction govern all the little mechanisms. So this kind of integration turns out shocked the community. The community start to think that there was almost a lawsuit. And then Brooke Benjamin and Fair find that the Stokes was inherently unstable. Yeah, and and later it was found this instability was a special case of Phillips' third-order interaction. By that, a new era of wave research started. Yeah, so the new modern wave research can actually be traced to 1960 when Professor Phillips published that paper. In wave study, there are lots of giants. Yeah, but I think if we move 100 years, 200 years, you'll come back, you will see that the contribution of Phillips is bigger than all the other people because he actually established that the wave can have gradual evolution. Yeah. Now, so I was interested in the wave, and I derived the equation, and I said, well, I'm going to go find the result, find the experimental data to support. I generate the wave as regular as I can at the 3 meters, and I watch the wave propagate to 4 meters, 6 meters, 7 meters, 9 meters, 10 meters. It's disintegrate, just like the National Physics Laboratory. So that's not new anymore. Okay, everybody know that the wave eventually disintegrate becomes that. Now, what is interesting is that when I took this data, instead of just look at the spectrum with the sideband instability or whatever, I did not use Fourier transformation. I used Hilbert transformation. And when I look at the Hilbert transformation, I was shocked. I found the frequency is not constant. Okay, I found all different things. So that's how I get into HHT. Yeah, I don't get in HHT of total vacuum, but I did not move as regularly as I presented now. Says, okay, I look at the frequency is not constant, therefore I went to HHT. I actually made a lot of mistakes. And to correct the mistake, using Hilbert, Hilbert has been used by other people, as I say, but the mistake I made actually saved me. Yeah. So based on Phillips' resonance theory, then the Hasselmann formulated it in spectrum shape, and then meanwhile TRW group, Lake and Yuan formulated the wave evolution in the nonlinear shooting equation. That's the perturbation derivation by Lake and Yuan in 1975, 1978. But even though they are the most famous group, they established the Schrödinger equation, and they actually demonstrate Fermi-Ulam-Pasta recurrence, and that is a generated wave. It disintegrates. It will come back to sine wave again. That's amazing. They almost demonstrate that through spectrum, but not knowing that when they actually demonstrate that, the wave has already changed. That escaped them. They did not pay attention to that. Anyway, using this formula, and you derive even go to high and higher order, you find that the wave instability even can create this like a fish scale pattern. And that also in Phillips nonlinear wave-wave interaction, but you have to extend it to higher order, fourth order, including direction and all that. And but all this was fine because United States was the most published country. All this was fine, but they didn't know in Russia, Zakharov, Vladimir Zakharov. In 1966 and 68, he has derived this nonlinear shooting equation totally independent of the shallow water equation. He derived this from Hamiltonian. It's much more elegant and much more complete. And that was published in the Russian literature. Nobody knew it until in the 80s. In the 80s, because of the Cold War, the United States government spent money to get all the Russian journals to translate that all in English, because not many people read Russian. So once they translated in English, they found that, gee, they have already done it in 1966, Zakharov. So they derived that in 1966, and actually it's governed. Schrödinger equation, as I said, is a function of A. A is the amplitude. It's not water particle. Okay, and they find that the amplitude is a soliton, at least to that order of approximation. And meanwhile, if you look at the soliton solution, that means this wave can actually have this. This is a this shape is a hyperbolic cosecant solution. This is a soliton solution. A lot of wave looks like this in the open ocean. Come a group. The group can be formed by wave of near frequencies. If frequency 1 and frequency 2, they are very close, then they have beats. But then the beats should have periodical structure. Like you go to the on the ocean beach, then a lot of people say by rule, every 7 waves is the biggest wave. So you wait, the first wave small, second wave little bigger, and the seventh becomes bigger, and then wait for another 7 wave, it'll come back. That's group. But this is not group. This is soliton. Actually, in shallow water, the lot of wave becomes soliton. So because of this soliton wave, there are people proposed to use soliton as the base to do spectrum instead of use sinusoidal. The water wave, we know that it becomes nonlinear Schrödinger equation. So once they know the nonlinear Schrödinger equation in the 70s, in 1979, Christian Desti, he's a professor from Norway. Right now it's at Bergen. At the beginning he's at Trondheim. It's Trondheim, and he was visiting the United States, and he derived the nonlinear Schrödinger equation to the 4th order. That's amazing. You start with this. Here is the governing equation. The water wave's governing equation is very simple. Laplace equal to 0. Incompressible, inviscid fluid. But the problem with this solution is the boundary condition. At z equal to zeta, you have this. This is a dynamic boundary condition and kinematic boundary condition. So use this boundary condition. You go through all this math and expand it, and eventually you derive this equation. This equation is what you call the nonlinear cubic Schrödinger equation to the 4th order. This is the cubic term. This is the term that makes all the trouble. Yeah. Again, in this solution, frequency is also constant. All this constant frequency assumption really make me become doubtful of the validity. Yeah. So the carry are assumed to be of constant. The constant frequency assumption, I think it's not right. Especially after I have examined the wave. It's not right. And I've been saying that ever since the mid-90s. Now it's already 10 years. The wave people still haven't paid too much attention, even though I got a couple of papers published to that effect. So last winter, when I went back to Bethesda, I went to pay Professor Phillips a visit. I spent 2 hours making a presentation to him. I pointed out all the inconsistencies. Yeah, I asked Professor Phillips. I said, Professor Phillips, I see all this problem. If you can solve this problem, then I'll take it. If you cannot, then I think we ought to at least announce to the community that the wave is not without any problem. The wave solution we have now, it's all based on very, very unreasonable simplification, I think. Yeah. When I say unreasonable, I was a little bit more strict. The wave equation derived as we have now describe lots of phenomena we observe. Yeah. But the theoretical foundation is wrong. I think right now people study wave. They are not studying wave. They are studying mathematics. And that's why the leading theoreticians in wave are all applied mathematicians. Yeah. They don't pay any attention to the physical phenomena. All they want is to look at the equation. But this nonlinear, the Schrödinger becomes, because Schrödinger is such a big name, it's hard to shake. The moral of the story is that everyone try to link their work with somebody famous. I am not the exception. For example, HHT is called Hilbert transformation. Do I use Hilbert anymore? Most of the time I don't. Many people at the very beginning suggest that we should kick Hilbert out of this the whole operation, but I still maintain it because that gives me a connection to the mathematical community. Yeah. So I criticize other people, and I should also criticize myself. Yeah. So most people study wave are actually study mathematics. Yeah. But it's physics that we actually should understand. I think a new start, something new in the wave has to happen. And so when I saw Professor Phillips, I challenged him. I said, maybe he ought to write a paper. He said, no. He said he didn't observe all this. I said, maybe we'll write it together. I said, well, let me consider it. So I start to air my view now to the wave community. Ever since I started to do Hilbert transformation, I did not do wave study anymore because I lost my faith in the lost my confidence in the wave study. Yeah. Now I think I want to turn around and tell the community, look, we have a problem. How can we clean up the problem? I don't have a solution. And that's the problem. But I do have the tool for you to see what is correct, what is the real physics. Now maybe you will see once you see the physics, you will actually agree with me and try to find a solution. There are lots of smart physicists and lots of smart mathematicians. I think once you pose the problem correct, the solution will come through. I will not discuss the details of the wave because that's part of our course. We will study that later. So once we get the Schrödinger equation, I know the envelope, I start to explore the envelopes. Yeah, the natural way to do that is to Hilbert transformation. Now once I use Hilbert transformation, I find a lot more than I asked for. In a way, it's not unlike what the Bush went to Iraq. He thought it was a simple solution, and he went over there and get mired into this terrible mess. Yeah, it's same to me. I thought, gee, Hilbert transformation is fine. I'll use it, and once I use it, I find more problems. Yeah, it opened up a new viewpoint, not only of water wave, but of the whole world for me. Yeah, and that's the reason I will share that in the rest of this semester. Yeah, so this is almost a conclusion of the first 3 lectures. By 1990, I finished all this probability study. I finished all the spectrum study, and I thought I have the ocean wave. I understand the ocean wave very well by 1990. Yeah, but then I get into study of the Schrödinger equation, and then I find that the Schrödinger equation involves amplitude. So I start to use Schrödinger equation. But in that effort, I use Hilbert transformation to study the laboratory data, and I made a mistake. What's the mistake I made? I took the laboratory data. I just make a Hilbert transformation, because when I studied the book says Hilbert transformation exists for LP. That means the equate any real number of function you can raise to the p's power, and the integral is finite. Hilbert transformation exists. So I said, well, that's fine. Hilbert transformation exists anyway. So I made a Hilbert transformation. I have a real number is my data. I made a Hilbert transformation, get the the analytical counterpart. Okay. So with this tool, I can compute the phase. I take the derivative of the phase. I get the frequency. That's simple, and that frequency shocked me. It's already very, very new. However, so I present this to Professor Phillips. He liked the result very much. Yeah, and then I went to Caltech and give a seminar, and I still remember the reaction of Professor Wu, who's a very famous applied mathematician and fluid dynamicist. He liked it very much. He immediately said that, listen, don't publish the paper anywhere. Give it to me. I'll publish it in the, in the Advances in Applied Mechanics. That's a very prestigious journal. Unfortunately, the impact factor is probably not that high. The 2 editors, fluid mechanics side is Professor Ted Wu at the Caltech. The solid mechanics, applied mechanics is fluid and solid. The solid mechanics is Professor Hutchinson at the Harvard University. So this 2 famous professors edited the whole series. Each year they put out 1 volume. Yeah. So Professor Wu told me to give my paper to him. I thought that was an honor, so I gave the manuscript to them. I was very happy, conceited that they come back. And I talked to other people. Other people say, well, look, listen, this may not be totally right. You take a water wave, you do a Hilbert transformation. But any function Hilbert transformation exists, but the derivative of the function may not be right as the instantaneous frequency if the water level is not exact 0. Yeah. Water level, how can water level be not exact 0? Yes, in the tank it has sash. The water level may not be exact 0. Yeah, and another complication is that what if wave has other bumps in that, not exact narrow band? So when I found this, I play with a little bit math. I found that the criticism was right. So I called Professor Phillips, Professor Wu. I said, well, I made a mistake using Hilbert. Could you give the paper back to me? Professor Wu will not do that. He says, no. He says the result is good enough, okay? And it looks reasonable, and whatever mistake you made must be minor. I'll give you 2 months to correct it. After 2 months, I will send this to the printers. So I had a very terrible 2 months because how can I correct that? I don't know. Yeah, I don't know how to correct it. So I was thinking about this day and night, and one day it dawned to me. It says, well, if the wave is not near zero, can I move the wave to zero? And how can I move to zero? And that is the beginning of the empirical mode decomposition. Yeah. And at the beginning, I start to walk. And then later, once I find the method, I look at the different phenomena, I start to run. Yeah, and that's what we are today. Yeah, the method is still new, and we're still exploring the mathematical foundation as well as different applications. So that will be the subject of the course. Start from next time, we'll talk about the real stuff. This first 3 lecture is my path, a zigzag path to reach here. It's all start from wave, but now it does not end with wave. It ends with all the other studies. Okay? So I'll stop here. Thank you very much. Yeah. Any questions? 台大有没有问题？哦，他们提前下课。只要静怡啊，静怡有没有问题？静怡的人都比较客气啊，他们比较。Okay. Any question here? I can't believe that my explanation is so good. 你们 You can ask question in Chinese. 问我用中文问 Okay? It'll be easier. I have an experience I will share it with you because we still have 10 minutes. I went to Beijing, give a talk on HHT. First time I used English. After my talk, there was absolutely no question. And then I was invited to the Academy of Science graduate school. I used Chinese. There was lots of questions. My talk is covered more than an hour. The question is also more than an hour. Okay, so the day of my departure, Peking University asked me to give a talk to their math group. So I went to the math group. I posed a question at the beginning. I say, I have given this lecture twice in Beijing. Here is my experience. I use English. Everybody understand perfect. Nobody ask question. I use Chinese. Lots of questions. So apparently, my English presentation is more clear. My Chinese presentation is totally unclear because people ask all kinds of questions. So what do you want? You want a clear presentation or unclear presentation? Everybody say unclear presentation. So I made an unclear presentation in Chinese. Sure enough, I have a lot of questions. Yeah, and I'm afraid my English is much better than Chinese, but unfortunately, I know my English is my second language. It's not that good. But it turns out that everybody understands me perfect. No question. Well, I'll count to 3. If you have no question, will not keep you. Oh. Okay.
Sir, you say that most problem they use
为什么？ Yeah.
他们用了太多简化的结果，可是为什么他们还可以得到相当合理的现在的结果？
Yeah, a lot of science and engineering. I will later will get that again. We never look for absolute proof. We look for close enough approximation. Yeah, the linear perturbation is close enough to explain the majority of the phenomena. But there are phenomena they cannot explain. That means if you can explain some phenomena, you are already successful in science and engineering. Yeah, but you may not explain everything. See, that's why science is moving, always moving one layer on top of another, on one layer on top of another. But mathematics is different. Mathematics, once they proved, that's it. For example, like I used the example of the plane geometry. Nobody can improve Euclid. Yeah. If we invite Euclid back here, and he will sit among all the mathematicians in plane geometry, I don't think anybody can teach him a lot of things. Yeah, because his geometry is so perfect. He may not solve all the problems, but once he knows how you draw the auxiliary lines, then he immediately will see the lights, and he can prove it too. Yeah, but if we invite the greatest scientists like Socrates or Aristotle, will come over here. Even an elementary school teacher can teach him a lot of things, like the Earth is round, the Earth is rotated around the sun, and so on and so forth. So science is keep on building. Yeah. Before we know Earth is not the center of the universe, we use Earth as center of the universe. We expand a lot of things. Yeah, to the degree of observation.
所以我们现阶段的工作只有用一些工具把非线性跟那个 non-stationary 展示给大家看，跟大家讲说以前这些都被忽略掉了，这是现阶段的工作。
Right. But right now, we do not have a total theory of, say, for example, if we give up the perturbation analysis, is tell me if I perturbate the frequency, I derive the equation, but I don't know when to stop. Is the first order non-constant or second order non-constant? Then the solution will be different. Yeah, and also you can make the equation so complicated nobody can solve it. So even you give that equation, the mathematician still kick out a few terms and get a solution. Yeah. But the computer is very powerful now. The computer helped us at least to see something. Yeah. Increasingly, mathematicians start to accept numerical solutions. Yeah. So if you can get a numerical solution, it's fine. Yeah. Okay. Yeah, we will talk about the Hilbert transform.
Because I look at most of the textbook is only about like 1 page, 2 pages. Here is how about the first word Hilbert.
Last time thinking back, last time I taught this course, I spent too much time talking about Hilbert transformation. To do that, we have to know Fourier transformation. Hilbert transformation actually is implemented by 2 Fourier transformations. And that was the invention of Gabor, who is a Nobel Prize winner again. Yeah. I think I have second thought of how much time I want to spend. I will talk about Hilbert transformation. Yeah. But I think since back deep in my heart, I'm already give up Hilbert. so I will talk about it, but not to a great extent. Yeah. We can show you to prove to you that the Hilbert transformation is two Fourier transformation back to back. We'll talk about that much. Or you can use convolution to compute the Fourier Hilbert transformation. Hilbert transformation is your data convolved with 1 over t. Yeah. So 2 ways to do it. Okay. Any more questions?
请教一下为什么就是 water 跟那个 ocean 是这么重要？有以前这么多人在研究这个部分的一个主题。
Well, 有 cultural 的 reason， 有这个scientific reason。cultural 的 reason 是，当这个when science developed, at that time, it also coincide with the sea power. Okay, in the 18th and 19th century, whoever controlled the sea controlled the world. So that's why the British is so strong. Now, before British, the Dutch was strong, and the Spaniard was strong, the Portuguese was strong. Then finally, British beat them all and rule the waves. So whoever ruled the waves ruled the world. So British was able to, England was able to establish so many different colonies and make it so strong. So everybody used the sea, and the ocean is important. So understand the wave becomes a important topic. That's cultural reason. Scientific reason, as I said, the wave, the motion, in the wave motion, the viscosity effect is very small. And if you neglect the viscosity, then the wave motion, the water motion, can be treated as a perfect fluid without the without the viscosity. Then the perfect fluid solution can be reduced to potential flow. And potential flow is much easier to treat mathematically, Laplace equation. Yeah. The boundary condition is difficult. But so since it's boundary, so we'll perturbate the boundary. Turns out the boundary is wave. Yeah. So you perturbate, you use that simplified equation, but that mathematically it's still treatable. Yeah. That's why wave at that time in the 19th century get so much attention. Yeah. And to this day, most of applied mathematicians still working on wave problem. Yeah. So if you work in, say, general circulation problem, general circulation, you cannot make any approximation. You have to solve the whole Navier-Stokes equation. But the wave is different. Wave is to say, well, sure, Navier-Stokes equation. Navier-Stokes equation, we reduce that as a dynamic boundary condition. We solve the Laplace equation. But in perfect fluid, in real fluid, we don't have that. The viscosity will generate vorticity, and that causes the complication. Yeah. Okay. All right. Thank you very much. Yeah. We'll start from next week. We'll talk about the real thing. 这个好多了，我不要拿着那个听筒。